Good afternoon, colleagues and visitors. My name, as Lynn said, is Cam Donaldson. I'm Pro-Vice Chancellor Research here at Glasgow Caledonian University, and it's my great pleasure to welcome you to this latest in our series of professorial lectures. This is a series that reflects the public role of universities, which for Glasgow Caledonian University as the University for the Common Good is about how our research and our teaching contribute to the Sustainable Development Goals issued by United Nations in 2015, running through to 2030 and adopted by all countries. And today the focus is very much on SDG 7, affordable and clean energy, SDG 9, industry, innovation and infrastructure, but with potential for impact on multiple other SDGs, as you will see. These professorial lectures present an opportunity for recently promoted professors to showcase their previous work and their future plans to colleagues, other stakeholders, and to friends and family. And Emad has his family with him at home today and also connecting in from elsewhere. And we're also joined by his ex-supervisor, Professor Ganem Putros from Northumbria University, and Professor Mohsin Almadi from Cairo University, who is also Executive Director of the Egypt Higher Education Reform Project, and who I know is very special to Emad. You are all most welcome. I'd also like to thank Emad for taking up the opportunity to present his professorial lecture online, not our usual circumstances in the past, so it's very much appreciated that he's taken on that small challenge. And so to Emad himself, Mohammed Emad Farrag originally studied for a BEng in Industrial Electronics Engineering, graduating in 1990. Followed by an MSc in Automatic Control from 1993 to 96, both through the Faculty of Electronics Engineering in Egypt. Emad has a PhD in Artificial Intelligent Control of Power Systems, having conducted an investigation of advanced control of the Unified Power Flow Controller in the School of Engineering at Northumbria University at Newcastle, graduating in 2002. And from 2002 onwards, Emad then held posts in both government and in academia, commencing as a lecturer at Helwan University, followed by a post in the Egyptian Ministry of Higher Education, before moving to a postdoctoral research position at Northumbria University and a research fellowship at De Montfort University in Leicester. In 2010, Emad came to GCU as a lecturer, was promoted to senior lectureship in 2014 and a readership in 2017. His research and capacity building activities on energy storage, power quality and battery management has attracted multi-million pounds in funding from, amongst others, the European Commission, the Royal Academy of Engineering, the Newton Fund and the Scottish Power Electricity Network. Emad's work has been published in top international energy journals, prestigious IEEE journal outlets, and referee conference proceedings in power engineering. More specifically today, Emad is going to explore how energy storage systems are helping shape a better life in rural areas in sub-Saharan countries and can be very beneficial for household income and be independent of the grid. He will also shed some light through that on health and safety issues. So without further ado, please join me in welcoming to the screen to present his lecture on Storage is the Key, Professor Mohammed Farrag. Welcome, Emad. Over to you.
Thanks very much, Cam. I wish you can see my screen at the moment. Great. So thanks very much, everyone. Thanks, Cam. And I'm glad to be given the opportunity to present the storage as the key for the future. And I've put the title from the Great Pyramid to the Greater Glasgow. So Great Pyramids because this is the area where I brought up and used to play during my childhood. So probably have enjoyed the video that been sent earlier on and you'd like to attend one of the New Year Eve in the Sphinx and pyramids. This is the top from the Greater Pyramid. In here, it's not a matter of 146 meters. My point is actually this road in here takes you down to Sphinx. And this road is very, very steep road, is one direction as you can see from here. And this is where we used to play during the childhood. You may have seen this kind of picture here, but this one may be amazing to you. So he's trying to balance the load by adding the school bags in the front. But you will be surprised to know these four people are going down the hill from the pyramids to the Sphinx in here as we used to do in our early ages. This is so long ago. Right, so maybe I ask you to have a pen and paper next to you, so probably you will be doing some exercise for me. The main idea for the pyramids is just to store the mummies for the king and the queen, but no one knows where exactly they are. And if you walk inside the pyramid themselves, actually cannot walk because the maximum height for the corridor is less than 1 meter. So you have like to crawl down the corridor there. And despite all the technology, no one knows exactly where they are. We have to think about they bought the mummies after they have already died and the pyramids been built. So how they get inside to put the mummies. Anyway, this is take you just off-site to relax. I'll give myself a minute to relax before I go to the challenge. So the lecture for today will include some items regarding the background and history about myself and a debate regarding is really green energy as a green or not, and what we need the energy storage for, and what is the most prominent energy storage form that we will be using at the moment and in the future as well, and its relation to the power system. Will shed some light on the electrical vehicle rules, considering the incentives coming from the UK government by 2030, 35 and 2040 that you will never have a petrol or a diesel engine on the market. So if you want to know how old I am, yeah, I'm coming from a 5-year BEng program. And when we had the exams in the morning and in the afternoon without a complaint. So you can imagine how old is this. And I've done a master that is with a norm in Egypt that you have a 1-year courses plus a 3 to 5 years research that a publication is a norm. Then I moved to do my PhD, as Cam mentioned earlier on, at Northumbria University, and I've worked on one of the FACS controller device called the Unified Power Flow Controller, and we managed to develop the first machine learning AI-based controller. For some people, this like just a block diagram of things that does not make a sense for someone outside the electrical power. But this simply means they have two controllers, and these two controllers, one series, one shunt, and they split into 4 parallel controllers. So these 4 parallel controllers need to work simultaneously, and we have to design a machine learning, artificial intelligence based controller for all of them. So you can imagine how much time you need to run 4 controllers simultaneously at the same time. When I listen to some other colleagues using machine learning and image processing, that they are luxury because the time is not taken into consideration. They can let the computer run and give them the results when the computer wants to do. But for us in the electrical power system, that is something completely different, because we are speaking about a response in a few milliseconds. So a 200 millisecond is a huge time for us. So developing a neural network-based controller that was developed to run online in a real time was a big challenge at that time during the 2000 or 1999 until 2002 when I finished. So one of the most important things that we have to adapt the parameters of the neural network to make sure they can respond to the changes in the power system. If you want to make it even complex, you want to go for adding a fuzzy control that needs a lot of calculation. So neural network and a fuzzy has been used, and we managed to reduce the operation or the calculation time to the minimum that suits the changes needed by the controllers, the 4 controllers running at the same time. Now you have a function for your paper and pen. This is not your Easter eggs, but you can consider this if you like. And this is we need to develop a machine learning based for you can get your brain working to count the eggs in this basket. The constraints, if you count them in a set of 2, the remainder will be 1. If you count them in a set of 3, again, the remainder is 1, 5, 4, 5, 6, remainder is 1. But if you count them in 7s, there are no remainder. So how many eggs in the basket? This is for you till the end of the lecture. Right, now we want to the debate. It's a big debate around us for and against, as really the green energy as a green. So we can see from this, the conventional, the nuclear, the coal, and the natural gas, the oil, we all know this is not environmental friendly. And we think that wind, the solar, biomass, and all of these are environmental friendly. I'm not the person who like to exaggerate things. I like to be moderate and put things in the right place. So as a really green, the wind energy and solar, let us go through the definition. What is the renewable energy coming to be our green energy? We said it does not pollute both air and water. So this is our definition. And is this really the case or not? You can look at the debate of, for example, take one example here, not all of the renewable sources. Well, take the wind energy, for example. So yes, they are fine. They do not emit CO2 while they are operating, and they do not require cooling for using water, for example, like the nuclear stations. But in the other thing, the people against it, they say, oh, okay, this is visually unacceptable, and they can hurt the birds and the and all of other life species in here. So they can make a lot of damage to the environment as well. And if they have lubrication leaks, this is again as a problem. But not, to be honest, this is not the only thing that the people against the renewable energy and its format, they think about this. They also think about the CO2 emission, because we say we want to use the renewable energy for reducing the greenhouse gases, the CO2 especially. So they said, okay, if you want to build a wind turbine, you need the tower, you need the nacelle, you need the generators themselves. So for every 1 kilogram of big iron, that you need to actually produce a 1,350 kilogram of CO2 just to move from coal to or coke to iron. And then if you want to change the iron to steel, then in this case, you are emitting another 1,460 kilogram. And if you want to build the foundation for the wind turbine, you need to use cement, and then you use CaCO3 or calcium carbonate and other materials. And again, in 1,500 degrees Celsius, you still produce around 1,000 kilogram of CO2. Not just producing CO2, you always consume a lot of air for the process. So it is not actually a clean energy source. It is clean during the operation, but not during the manufacture. You need all of this to generate or to build the blades, the generators, and the cell. One of the most important things that people do not look normally at it's the radioactive materials when you produce renewable sources or the machines, especially for the PV system, the solar system, that the radioactive material is huge, and it has an impact on the climate more than maybe the CO2. So people still in the debate against and for. So one of the people for the renewable energy said, okay, despite all what you have said before, it can emit only between 15 to 12 CO2 per kilowatt, for comparing to the coal, which is 620 gram for CO2 per kilowatt hour. So still there's a big debate. Someone will say, yes, that's maybe right, However, what about the installed capacity of renewable resources against the operational capacity? If you install 100 megawatt, well, you take 100 megawatt of the wind turbine, of the wind energy. It is not. So this numbers 15 and 12, it's not the actual number for the installed capacity in this case. The debate will continue, will never stop. So I'm not, as I said, I kind of look at the moderate thing. So I don't like to use green or non-green. So I would like to use, is that beneficial to us or not beneficial to us? Is that least beneficial or most beneficial, rather than going to the extreme sides of good to the environment or not good to the environment? Right, this was a kind of the debate regarding the renewable, against the green or not green, but we have to use renewable. There are a lot of benefit of using renewables. It's not producing as much as CO2 as other ones, the conventional resources. Then if we are considering renewables, I will consider only one example here that we worked on over the past few years. This is a real data from a site that near Prestig was one of the projects we worked for one of the companies to install wind turbines, and we studied the feasibility for them to have a wind turbines installed. So as you can see, the variability of the wind speed over the months of the year in here. It is fortunate for the UK because the peak load in winter and the less load in summer, so with less wind and summer, of course. So this is okay from the profile point of view for the wind. However, over the 24 hours, the wind speed is variable as well. And if you look at this one, again, for the same site, the wind speed is high, around 14 hours, so 2 o'clock afternoon, which the load is actually less as the off-peak load time. For me, this is the issue in here. The issue is during the peak time load, the wind energy produced is less. So we are not getting the most benefit of even the installed capacity that we have if you want to match the load. So if we change it from a scale or increase the scale of the wind turbines from 0.5 meg to, for example, a 2.5 meg 5 times, you will never produce an energy like 5 times. So just increasing the size of the wind turbine is good. Of course, you will produce more, but not as much as you think. As you can see in here, the maximum for a 5 times rating is only 3.6 times of the maximum energy can produce. Still the problem at this time when we have less energy produced from wind, but the load is maximum. So as you can see, these are the peaks of the loads. As you can see, the load nowadays, it's from National Grid for last month, the 22nd of February. The load is coming nearly flat nowadays because of the pandemic. It's not just as the normal load. The normal loads that we have peak in here and have a big trough in here during the middle of the day. But because of the pandemic, the load profile is changing. I'm not sure if it's going to continue like this. Hopefully there is no pandemic, but we will see what's going to happen. So during the peak time, the actual production of the wind energy is less, and during the peak energy, the use of this energy is less. So the engineers and the power system grid, they do not rely on this peak of the wind in here by itself because the load is less, and they tend to curtail the wind produced. And this is another project we worked with a final year student from one of a real site around us. So if we look at this one, they normally curtail the wind generation, they would normally curtail the wind generation to some extent. So they said 10 megawatts, this is the maximum you can produce. However, the potential, as you can see, is around 100 megawatts. So there is a loss all the time in here. There is some factors you can consider here. For example, this is early morning where there is no energy needed. This is the off-peak load. So the loss in here, because we don't have an opportunity to use this energy or to store this energy. As you can see, it is around 9,000 pounds per hour because of the curtailment in here. The curtailment is understandable from this graph because we have a good forecasting of the weather. So we know after 3 hours, the potential will be dropping because and when the speed is dropping. However, you still have this difference between the curtailment and the potential. So why we don't wait until it is really the less time or less production of the potential? Why we don't wait until here, even here? Why we don't use even this 18, 19 megawatt of energy produced by the wind farm, but we completely curtail this to zero? It is starting 6 o'clock in the morning, so the load will start to be picking up and coming toward the first morning peak in this case. So we have a problem. We produce energy, we don't use them. There is other thing that was the wind energy is called the capacity factor. If you want, for example, to have a 300 megawatt, you have to install 1 gigawatt of 30% capacity factor of the wind energy. So you cannot produce a 1 gigawatt all the time. But if you compare this to the actual thermal or the conventional one, you only need 350 megawatt with a capacity factor of 85. So the debate about, is that useful for us to use the wind energy, for example, or renewable energy as it is in this case without any sort of energy storage? The question will come, can we actually increase this capacity factor? Can we improve the efficiency of wind turbines? Can we reduce the curtailment? We can reduce the curtailment, but we can increase the efficiency, and this is the point of research every day. However, we still cannot make sure that we can store all this energy until we need them, because we cannot align the energy production to the load. To give us a sense of what's happening in the future, we look at the power system, and this is well known to everyone working in the power system. Like if you are driving your car up to the hill in here, the first thing you notice on your car that the speed is reduced. And this is what happened in the network. If the load is increased, the frequency is reduced. And we want to make sure that this is balanced all the time. And when you increase or decrease the load in the network, the frequency is fixed. So every synchronous machine, which is the normal conventional power plant, we have a power system stabilizer that we can adjust the frequency back to the 50 hertz in the case of the UK. But can we balance this load, the change in the load externally? Can we add loads or can we add sources when we have more load? Or we can shed some of the loads when we don't have extra resources? So between controlling the loads and adding resources, this will be our research need to come and introduce new ideas. So taking this further, that we have what's called deferrable loads. So can we adjust the loads to come another time? So for example, starting from your washing machine, can you get your washing machine to work when there is the PV system you have in the roof that producing energy? So most of the technology at the moment, washing machines can start from the point they stopped. They didn't have to repeat the program from the beginning. But there is on a large scale one, there is a technique called the demand response that the National Grid sign a contract with a big factory that they can disconnect this during the peak time or during the emergency time. So can we do this with the energy storage that will support the renewable energy in this case? To do the load deferral, we have to have a very good forecast about the loads, about the weather, about so many parameters. So it does not look like a feasible solution in this case. So let us think about something different. Instead of changing the load, we want to see how we can make the load flat load. So these are typical distribution network load in the UK. So during the peak time, we want to have a source which can be discharged during this peak time and can be charged during the off-peak time. So we will need for definite in here the energy storage that can phase or can align the renewable energy generated power in here to match the load using this energy storage. So energy storage becomes a vital support to the network. So many energy storage programs and techniques are used at the moment. So they can be used easily because they can top up or drain based on the load or based on the production from renewable sources. They can support the integration of renewable energy. And also for some people, they can make an income. So for example, if you have a rooftop PV system and producing a 4 kilowatt, for example, you can give this to the grid, get some money, and then you can this to pay off your load during the peak time, or you can use this in other areas. One project we applied last month with Kenya is to improve the life for people in Victoria Lake to the fisher. The fishermen people, they get the fish in the morning and they have no electricity to support them in this early morning to transport the fish to the market or to keep the fish in a mobile refrigerator. So we are doing some project with them. Hopefully we'll get this accepted early next month. But from the storage point of view, there are so many storage mechanisms. One of them is the mechanical one, and I'm sure most of you in Scotland here know this. This is the Crookham Dam. This one is being built many years ago, built at the same time at the Hunterston A. Hunterston A is now demolished, decommissioned as a nuclear power station in Hunterston. Now it is Hunterston B and Hunterston C comes in the future. So mainly this one is using the extra energy produced by renewable sources in Argyll and Bute, especially the wind energy, to pump the water up to the reservoir during the off-peak time or during the energy produced by the wind, and then they will release the water down to compensate or during the peak time. The other sources that you may heard about it, the hydrogen now in Europe or in Scotland and some other places in the world as well. The hydrogen, whatever it is a green or a blue hydrogen, it is produced by using renewable energy or produced from the hydrocarbons. So it is big projects, and probably have heard about one of the biggest projects in the Middle East to come, Neon City in Saudi Arabia. This is one of the big ones. We have one small one at GCU. Actually, I'm not sure how many of you visited the CHP at the backyard between Charles Oakley Building and the Governor Beakey. This CHP is actually producing the base load for GCU most of the time, and also the heat for heating the all the buildings. But I will be focused more on the chemical or the batteries kind of storage for this case that we have been used. To give you an indication how many kind of projects in the using batteries in the UK, this is one for 588 megawatt was just one company in the UK, and so many other projects are running. So we will reach over the 10 gigawatt of battery energy storage. Last week, Dundee approved a 50 megawatt just by the roadside battery energy storage. So these are coming to be more effective in the grid. I'm fighting the time actually. So just to quickly through what is the impact of renewables integration. So that will explain to us why we need the storage. So for example, from the impact of the renewable energy, here there are three main areas: the stability, the flexibility, and the adequacy. From the stability point of view, when we add more renewables, that's the converter-based or inverter-based integrated to the grid, we have an issue, a critical issue with the reduction and the kinetic inertia and the grid. So the kinetic inertia is the mass and the rotating machines and the synchronous machine. When we have more renewables based on inverter connected to the grid, then the changes that happen during the change of the load or the faults, this will not be counterpart by the kinetic inertia and the mass. So we have a problem with the renewable energy in this case. But however, the researchers started to look at this and they tried to use the renewable itself to support the grid, to support the frequency, and to produce more reactive power to try to keep the voltage within the limits all the time. So this has come through the flexibility of using renewables in this case. The third parameter is actually the adequacy. We know during the peak time, especially overnight between 6 o'clock and 10 o'clock in the UK, we have a peak time. And then we have to switch on some of the synchronous machines that can be switched on and off quickly, maybe within 10, 15 minutes maximum, to cater for the peak load in this case. With the integration of the renewables, in addition to the storage, there's the synchronous machines in this case used for peaking the loads to shift the load at the peak time. They will not be able to recover their investment actually. So there is a threat for the existing synchronous machine at the moment from including the renewable energy during the peak time in this case. Nevertheless, it's not these only the impacts of the renewables. There is some other from power quality issues. So all of the engineers, they know all of these things. One of the projects that we have developed with one of the PhD students, finished now with a colleague. So we can use the storage with the renewable sources to improve the frequency during the fault or during the changes in the load based on the lack of the inertia. So as you can see, the frequency is dropped massively in here, and we managed to put it back to within some limits. It still need to be improved by using the energy storage elements that are switched on the grid during the fault operation or during the changes of the loads. Another thing that we looked at as well, using the integration of renewable sources, mainly wind and PV system plus the energy storage, is to maintain the power and the grid to prevent any reverse power from the renewable sources back to the grid. So you don't need to change the infrastructure of your distributed transformer in this case, and you can keep the transformer as is, and then you can charge and discharge the batteries to accommodate the extra energy produced by renewable sources. We did a lot of work in here to optimize the location, the size, and the site of the energy storage and the wind energy or the renewable in general. Another project that we worked in is to design a smart transformer for the distribution network. We all know the voltage need to be within a certain limits. So to keep this limits depends on how much is your energy generated in the distribution network over the load. If you increase the load, the voltage will drop. If you add resources like the distributed generator, then the voltage will rise. So keeping the changes of the voltage is not a good thing in the network. So we have to stabilize the voltage within those barriers, the red dashed lines in here. So we managed to design a smart transformer that can operate to control the voltages and all the bus bar, the downstream bus bar within the range using the energy storage as well. One of the other projects that we managed to get a good results is actually it can change the regulation, the current regulation. The current regulation, if you have a wind turbine and disconnected to the grid, if you have the loss to the connection to the grid, you have to disconnect the wind turbine. And irrespective, you have wind and you have local loads that you can feed in. But the regulation said no, you disconnect from the grid once the voltage here is dropped below certain limits. So we worked out what is the optimum loads that connected to this wind turbine to keep the wind turbine working irrespective of connection to the grid or not. We managed to get this optimum situation of the load. However, there is no guarantee you can keep the load constant all the time. So you have to make sure that your load is variable. And in this case, you manage to run the wind turbine at optimum load all the time. It still have the risk of disconnecting or adding dummy loads. So what will be the solution? The solution we have done is to run the wind turbines in this case, irrespective of the changes of the load. We managed to add an energy storage, battery energy storage, to be charged if the load is less than the production of the wind turbines, and to discharge during the time when the load is higher than the production of the wind turbine. So as you can see, the black line in here, the wind turbine is producing its own capacity all the time, irrespective if it's connected to the grid or not connected to the grid. So this one was one of the interested projects that we worked together. Probably you need a 1 minute break with this clue as well. Can you multiply these figures, okay, in one step without using your memory or the calculator? So probably can write them down and try to do it until the end of the lecture. So you don't have to use your calculator, you don't have to use your memory if you have a good memory, like I used to have like 30 years ago when I used to remember the whole class ID number was 9 digits. Right, so the transportation is known as the more enemy of the environment because it has produced 34% of the CO2. So electrical vehicles are soaring now in the market. As you can see from this graph, it is actually rising by 3 times between 2019 and 2020, and it will continue. The main concern for any electrical vehicle owner is the battery, because this is the most valuable asset in the electrical vehicle. They will say, okay, I don't want to use electrical vehicle. I cannot connect my electrical vehicle to the grid to charge, discharge them into the grid during the peak time and charge them during the off-peak time. I've taken this from the project that I followed closely, that run Horizon 2020 with Northumbria and other partners. So they just mentioned that instead of adding the charging of the battery of the electrical vehicle during the peak time, you charge them during the off-peak time and even use the electrical vehicle to be discharged during the peak time, so you have shaved the load in this case. The principle is there, but the people will be worried about their asset, about will I have enough energy in my battery so I can go my next trip or not? So with the development of the smart charging in here, that will be able to not to be worried actually about many factors that affecting the electrical vehicle batteries. You can change the speed, how you charge your batteries. If you need it overnight, that's fine. If you need it in 30 minutes, that's also fine. Also, you can control the power that you pump in your battery. You can just control it from your mobile phone. So also you can align this to the energy cost. So with the smart charging, shouldn't be a problem with having the electrical vehicle connected to the building or to the home or to the grid in general. So the other thing that we as electrical vehicle owners need to think about at the end of the life of your battery does not mean the battery does not have a value. You are not going to go and recycle this battery. Actually, you will recycle it, but for another use. So the energy storage will be using the second life electrical vehicle batteries as well. So for the researcher, the things are different. We want to make sure what is the value of the battery in this case. So we need to understand the battery degradation. the battery factors. Can we reach a situation that the electrical vehicle battery are swappable one, like the cylinder that we used to, butane cylinders that we used 50 years ago for cooking? Can we use the electrical vehicle battery, something like this? Can we swap them? Can you drop your battery, take another one, but you only trade the energy and the battery rather than the value of the battery itself? This is another project we are working on, but we didn't have much time to go through all of it. This is a recent project we started with a PhD student that regarding the identifying the state of health and the remaining useful life of the battery. So we identified the degradation mechanism, where are it coming from, and these mechanisms, how they can affect both two parameters or two main factors for the battery: the capacity and the impedance or the resistance of the battery. And these are the two variables here that affect the state of health of the battery and the remaining useful life of the battery. So this project in here, we managed to start with identifying the models or the chemistry of each battery model using the Gaussian process classification for the incremental capacity. And then we managed to go through all of these data analysis to identify what are the features that within the charging discharging cycle of the battery that will tell us more about the remaining life of the battery in this case. So this is a project that probably this is the second year for the project, and we are about to publish one journal paper out of it next month. This project in here is actually part of the previous project, but was a final year project. Probably one is attending with us, so I'm glad that he managed to kind of train a neural network of the resistance or the impedance of the batteries to identify. If you measure the impedance of the battery, then you apply it to this neural network, will tell you where is this from the life cycle of the battery. Are you reaching the 900 cycle, or you are still in the first 100 cycle of the battery? So it can give you an indication if your battery is coming to an end or still in the middle of its age, or it's too early for the battery. There's two projects that we are working and preparing for them, and probably will start in May. One of them is the large scale batteries as a storage will have a lot of problem from the intrusion, the cybersecurity of the large scale battery, as we've heard about the cybersecurity of the large BV farms in the past 6 months. So we will be working on this to make sure that what are the intrusion, how we detect the malfunction or the unuseful information that injected into the battery energy storage system, that we make sure that it's safe and secure for everyone. Quickly on the health and safety, that is a problem to have a pair of battery and under the stair if you have a BV panel on the roof. To me, it's not a problem at all. It is as safe as you travel in a box called the plane. Exactly the same. So the safety is very, very high, and the manufacturing of battery at the moment is not a big issue. How many billions batteries that we have in our mobile phones, and how many of them catch fire? So this is kind of the percentage that give us the indication that yes, safety is not an issue at this stage. Just to appreciate the colleagues that I worked with, and they now are colleagues or still a PhD student in progress. And I would like to appreciate everyone added a single value to my life. I would like to thank Professor Ganem Potros, as Cam mentioned earlier on. He was my PhD supervisor. Still until today, we discuss things together, personal or technical. And also much appreciation to my role model, Professor Mohsen Al-Mahdi. I learned too much from Professor Al-Mahdi when he was the executive director of the Egyptian Reform Project. You can imagine a project of $73 million. and he's dealing with, from their excellence, the ministers, the 17 principal and universities, 8 technical colleges, all the way down to the office boy at the end of the corridor. So transparency, fairness, all of these things I'm missing, and I learned a lot from him and try to apply it. So now probably you need to know the solution for your clues. This is for your Easter eggs. And this is how you perform the multiplication on one line. You multiply 2 by 8 and multiply C by the next figure, which is 4. 6 by the next is 7, 6 by 4. Put them together. This is your solution. A quick list of projects that I've worked at the moment over the past few years, and a future project as well, one of them from the Royal Academy. And thank you for attending. Thank you. I will stop sharing, Len.
Thank you very much. Is anybody wanting to ask a direct question? I don't have anyone with a hand up. So I will go to the chat, if you just bear with me, Emad.
They are very kind and they don't want to ask.
So due to the limited energy density and cost, do you think the use of batteries for grid support would be limited to frequency, regulation or more?
If I understood the question, I don't think there will be any limitation using the battery at a large scale to support the frequency and the network, or support the network during the changes in the loads or during the black start. Shouldn't be a problem for the battery from the dynamics performance of the battery themselves.
Thank you. I've got a direct question from Oli. Oli, if you're wanting to unmute yourself and ask, please. Thank you.
Yeah, thanks. Yeah, first of all, thanks very much for doing this, and sorry I was late. So my question may well be daft. You mentioned, Emad, the necessity to maybe put storage power quickly into the grid, which you could do through batteries. And I would just wonder if we're thinking of 100% renewable system, is there like a magic formula, how much battery you need, how much hydro storage, how much hydrogen tanks, or you see what I mean about how to level out all these peaks and troughs?
Right. First of all, you cannot rely on one source of energy storage. It's good to have different sources, so we are not prone to one of the difficulties or the challenges of one source. So you have to have a mix of all possible sources, like the pumped hydro or compressed airs or batteries. But the good thing about the batteries is that the charging and discharging time for the batteries is massively under control. So you can bump and the energy stored in the battery in half an hour if you need them, and then you can charge them again at the same time. So having all of these things working together to flatten the flow of the power and the grid is very, very important. And you cannot reach 100% renewable without the use of energy storage. No way. And also, you have to consider, if you have 100% energy storage with battery, you do not need to install the 3 times as capacity. So you may install only the 2 times or 1.5 times capacity of the renewable sources with the battery.
Thank you. We've got another direct question. Mohsen, if you'd like to unmute yourself, please. Thank you.
Hi, Dr. Emad. Thank you so much for this lecture. I really enjoyed it and improved my knowledge about the smart grid, renewable energy, wind turbines in short time. Thank you so much. Just I would like to ask, do you think, like, if we think about the hot countries, like the countries of North Africa, is it better to use wind turbines or solar cells?
Right.
Which one?
In North Africa, the most potential resources is the PV system, especially in the 2 West Northern African, Algeria and Morocco. They have the most suitable environment, the temperature between 25 and 28 all over the year, which is the best temperature for the PV system. But if you go deeper in Libya or Egypt, you should avoid the going deep again towards the Sahara. So you have to use only the very small strip on the northern coast. For example, there is one project in Egypt and down south for PV near High Dam, Aswan. But the temperature over there, it is not less than 36 by any means all over the year.
All right.
So PV on the north coast, the Mediterranean, the South Mediterranean is the best. Probably have heard about the European project, 43 billion euro project in Algeria and Morocco. They already started 2 phases. It's called the Noor in Morocco for massive PV systems in Morocco. And this will be connected to the network through the link between Morocco and Spain. Probably we can think about the cable carrying all of this electricity from Morocco back to Spain.
Should be a huge cable.
Put it in a pipe and gives them water in the pipe and they get electricity from them.
All right, good.
This is just an optimistic one.
Thank you. Thank you.
Thank you. We've got a friend on the chat.
Can I make some comments here? Hello?
Yes, please, Professor Mahdi, yes, please.
Dr. Emad, I am truly delighted to be invited by you to attend this lecture from a very dear colleague, and thanks a lot for saying such wonderful words about myself.
It's my honor working with you, actually.
Really, it's truly a delight. But don't you think you're wasting your time working in this research while you can be making millions of dollars in money with Tesla car industry developing their batteries? That's what one thing that I'm truly wondering. You can make a lot of money in this regard. The other comment that I wanted to say is that also Egypt needs your efforts because, as you know, we have one of the highest wind speeds in the world, and we are trying to focus on that, and we are developing also utilizing the solar energy in a much larger scale. In fact, we are developing the largest plant in the world currently. So what are your comments, and when will you be coming to support Egypt again, as you have been doing?
Thanks very much, Dr. Mohsen. Well, there's two things regarding the battery from Tesla. Tesla is using this for the cars, and with the research we are doing at the moment and the project I mentioned from Northumbria and Horizon, just to improve the usage of the batteries in the electrical vehicle to support the grid. So this is going to come to be a real one. So any investment in Tesla for producing different types of batteries and batteries that can have an energy to weight ratio is better than what we have at the moment, and the speed of charging, all of these will help in integrating the electrical vehicles into the grid. From the other point from Egypt, yes, Egypt has one of the largest wind speed in the Suez, the stripe of the Red Sea near the Suez Canal, and they have a wind farm there, and with some hybrid compound cycle gas as well. But from the wind energy plus the PV in Egypt, again, it is in the northeast rather than in the south. The south is too hot for the PV system in Egypt. This is my opinion, at least. But at the moment, Egypt reaches a saturation and production of energy. So any investment, they have to find a solution to sell this energy back to the some other countries. So that's why the linking now to Sudan, and Sudan will be linking to South Sudan as well. So you go down to Africa, and there is a link with Saudi Arabia that started last year, and a link with Jordan, and the link with Jordan will continue to Europe through Turkey. And the only area does not have a link is from Egypt to Morocco through Libya and Tunisia. So you can see now all the Mediterranean will have one circle. If they completed this project, that will be more beneficial to Egypt to implement so many wind farms or PV system in the North Coast. And I'm always happy to come back to Egypt.
Great, good news.
Thanks very much.
Thank you. I'll just quickly go on to a few questions from the chat. From Emad, what was the main unique features of your smart transformer versus conventional transformers?
The smart transformer we developed, it has a local controller that can measure the parameters and the distribution network, and then they take an action based on those parameters. So the normal distribution transformer is just bypassing the power from the high voltage to the low voltage without controlling or measuring any parameters downstream. The smart transformer has to include all the power generated downstream from distributed generation, also the bus bar measurements using PMUs.
Thank you. And we'll take a question from Babakali that he's sent over. How can the recycling of lithium batteries be managed after the end of life, and what impact will that have on the environment?
Right. Of course, they have a great impact on the environment if you completely recycle them. But we said with recycling of the lithium-ion batteries will be on the two stages. The first stage to use them in electrical vehicle, and then once they reach a certain capacity, you use them in energy storage. And in this case, you can increase their life. So you can use the energy, the battery, within a car, an electrical vehicle, for maximum 3 years, but you can use it afterwards and the energy storage maybe for another 5-6 years. So you are kind of delaying the recycling, but we will face a big problem, and by 2040, when all the fleet will be electrical vehicles, we'll have millions of electrical vehicle batteries that they need to be recycled. And this is our job as a researcher to find the solution.
Thank you very much. I'm just conscious of the time, so I'll just hand back over to Professor Cam Donaldson. Thank you.
Thanks very much.
Thanks, Lynn, and thanks to the audience. Obviously, Emad, you more than sufficiently have engaged the 70-odd people that have joined us tonight. So thanks to them for that. But thanks particularly to you. I for one, as a social scientist, learned a lot today. No less about some nice arithmetic tricks. I really enjoyed that, but obviously much more seriously, this whole, I learned a lot about this whole area of smart energy and its storage, which I think, and as you outlined, not only in terms of what we've achieved already, but in terms of the major questions that have to be addressed in the coming decades, is just of huge importance, and is going to occupy lots of important research time across the globe in the coming decades. So I, for one, would just like to thank you for giving the likes of me some insight into how important and imaginary your research has been, and I think is going to continue to be going forward. So thank you very much, Emad. Thanks to the audience, and hopefully you can all enjoy now a nice relaxing evening with your friends, family, and otherwise. Thanks very much.
Thanks very much, Cam. Thanks everyone for attending. Thank you. Bye.